Hey guys, my name is Hiraku Murakami. I'm here with NovaEdge Academics, and today we'll be covering topic B4 Thermodynamics Part 1. So, to kind of give you an overview, thermodynamics is about converting heat into useful work. Heat was always treated as, like friction or, loss or something like that in topic A. But here, we're going to study how we are utilizing heat in order to do useful work in the real world. A basic example is, an engine in a car or a steam engine in a train or a rail, right? So we're able to convert heat into useful work in order to move things in the world, and it's being used all around in factories and power generation and everything. So this is a really important topic. It also is probably one of the most relevant topic for engineers. You'll be covering it in mechanical engineering, chemical engineering, materials engineering, and all the others. Okay. So how does this principle work? How do we convert heat into dynamic work, right? Well, it follows the whole concept that we've covered in B3 about gas. It's about expansion and compression of gas. So when we expand gas, it actually does work on, let's say, the piston. So as an example, here we have a car engine, and I'm going to show you through a car engine how we convert heat into work, okay? So as an example, we have the piston coming down in first part, which is about intake. It's about taking in air and fuel. And after that, and it rotates, it's going to compress this gas, into this small volume. So it's pressurizing it. And when it pressurizes, it makes it easier to combust. So when you do a combustion, like give it a spark and you combust, the fuel is going to basically explode, and in that explosion you're going to be expanding gas and pressing on the piston to rotate further, and in this rotation you're going to have the wheel attached to here, so that wheel is going to turn with it, right? So essentially in this cycle you're converting heat that you're producing from this explosion into gas expansion and then into useful work, which is movement. Okay, and after that, you turn this on so that the exhaust can have the gas exiting, which is what we see in a car, right? So you have the gas, residual gas from explosion exiting this piston, and then it repeats the whole process again and again. And so this is one cylinder. Okay, and so what happens when you have 6 cylinders? Well, we call that the V6 engine. So I don't know if you're familiar with cars or if you're like into racing or F1, right? The cars will have, with the number of pistons, they'll be labeled V4, V6 engine. So that's corresponding to how many cylinders there are. Now, not just the number of cylinders that's relevant, it's also relevant as to how much gas you're able to compress. So sometimes it'll be like 1.6 liter V6 engine. That's corresponding to how much gas you can store in a cylinder and how much you're able to compress. Because how much you're able to compress and expand, that's relevant to how much work you're able to output from a heat source, okay? So let's talk about this more further into mathematics. So how do we quantify this work? Well, we've covered before this PV equals nRT concept in the gas law, right? Well, it's got to be something relevant to that because that expresses how much gas is in a certain volume, right? So the work done when you compress or you expand the gas is equal to pressure times the change in volume. So if I'm pressing it, then I'm doing a certain at a certain pressure, I'm doing some certain work. And if I'm expanding it, I'm also doing a certain work. Now, it depends on if you're in physics or engineering. Sometimes you'll call it positive or negative for either. But in physics, we're going to call expansion as a positive work and compression as a negative work. And the reason why is because when we expand in the cylinder, that's when we're actually doing work, right? That's how we convert it into useful work, okay? And so let's do like a basic example. Well, it's going to correspond to the area underneath the curve, by the way, in pressure versus volume graph. So as an example here, let's quantify how much work is being done in part A. So in part A, you're going to have the area is equal to, well, this area, let me call it A1. This is A2. So A1 plus A2, which is equal to 3.9 minus 2.1 times by 0.038 minus 0.017 divided by 2 plus by A2, which is just 0.038 minus 0.017 times by 2.1. 0.063 joules. Hope you got the same thing. You can also do the same thing for part B where you quantify it. Now this will be an approximation because it's not exact, so that's going to be the approximation. And one thing to note is that the works unit is joules. And you might be wondering, okay, well, that's pretty interesting. So PV here is actually joules, and nRT is also joules. So it's actually just work that's being quantified when we talk about PV equals nRT. And you're always free to try to check the unit. I'm going to show you how you can show the unit that's equals to joule right now. So P is Pascal, and V is this, right? Now, pressure is just force over area. So Pascal is equal to, well, force over area, which is Newton over meter squared. Now, F is also MA. MA is kilogram times it by meters per second squared. Right? And when you cancel this out, you actually get kilograms meters per meter per second squared. That's Pascal. Now, volume is meters cubed. So if I divide this by meters cubed, I'm going to get kilogram per meter squared per second squared. Okay? And so this is actually the SI unit for joules. Okay? And you can always check this in this methodology, how I just showed you. That's how you derive the SI unit. Okay? So now we've talked about how to quantify work in terms of expansion and compression of gas. So now I want to talk about the first law of thermodynamics. And the first law of thermodynamics is basically about energy conversion. It's the law of conservation of energy. When I have this much heat going into the system, then I'm going to have this much work being done, the balance of which has to equal to each other. Okay? But interestingly, there's another factor that we haven't talked about, and that's the change in internal energy. So as an example, right, if I have a beaker full of water and I put some heat into it, so that's fire. So if I put Q into it, we know that the temperature is going to go up. The temperature of the water can go up. And when we have an increase in temperature of something, we have an increase in internal energy. We've talked about this previously in topic B2, I believe. So check those videos if you haven't. So there's going to be a change in temperature, right? So there's two things that can happen. One is the heat that's being contributed can change the temperature, or it can also change the volume. So those are the two things. So internal change in internal energy is quantified by 3 over 2 nRT, or 3 over 2 N times kB times T. The change of internal energy is dependent on the change in temperature. Okay, so if the heat being put into the system causes change in temperature, there's a change in internal energy. Okay, you also have work being done. So that's something we've already talked about. So there's two things that can happen. Heat can turn temperature to different temperature, or turn volume into different volume. Okay, and we're going to talk about 4 main processes, thermodynamic processes, and why they're important. Okay, so the first one we're going to talk about is something called isobaric process. And iso means equal, and baric means pressure. So it means equal pressure process. It's a process in which you don't change the pressure and you change the volume, or you change the temperature. So let's see what the implication is. So first, we're going to heat up, let's say, a piston, right? When I heat up a piston, what happens to the volume? It's going to increase. It's going to increase, which means that it's doing some work. So we're going to have some work being done. But then also one more thing that's going to happen is it's going to change the temperature, right? So there's two things that's happening. One is internal change in internal energy. The other is work being done. And so isobaric process leads to delta U plus W. Okay, seems pretty basic, right? So you have a constant pressure to a change in volume. By the way, the area under here, that's work, right? So if you know the heat that you supplied, and if you know work, you can also calculate the change in internal energy. Okay, so why am I talking about this? Because other processes might only affect one factor while leaving the other 0. And so I'm going to talk about that next. So isovolumetric process. Again, iso means equal, volumetric is volume, right? So what's happening? We're keeping the volume constant, right? So maybe I lock the piston. I lock the piston so it doesn't move. So what's happening? Well, it can't expand or contract, right? So what's happening? Well, all of that Q has to go somewhere, and it's going into change in internal energy. So work is 0 because P delta V, which is P times 0, right? So all of that heat has to go somewhere. It's going into change in internal energy. So Q is equal to that. okay? And in a graph of P versus volume, it's expressed like this because volume is not changing, it's only one volume, okay? So now I'm going to talk about isothermal process. Again, iso is equal, thermal this time is temperature, right? So you're keeping the temperature equal by letting the piston expand on its own in a very, very slow and controlled manner, okay? And you might, and also, so the temperature doesn't change, so delta U, which is 3 over 2, and our delta T is 0 because delta T is 0, right? So all of the heat is converting into dynamic work. And you might be saying, wow, this is an ideal case, right? Because that's fantastic. The whole purpose of thermodynamics is to convert heat into useful dynamic work. So if all of that heat is going into useful dynamic work, this must be the best case scenario, and it really is. But let me tell you that this doesn't really happen in the real world, because for you to put heat in and expand this without changing the temperature of the gas, quite impossible. In fact, you'd have to do it like at a very slow and controlled pace at an infinite time, in fact. So this is an idealized case that you'll only be able to do just mathematical calculations and be tested on the exam. And last but not least, we have the fourth process, which is called the adiabatic process. And a lot of people get confused because this is not iso something anymore, it's adiabatic. And what this means is you have Q is equal to 0. Okay, so heat is 0, which means the system is completely insulated. You don't have Q going in and you don't have Q going out. So what does this mean? Well, it's about converting work into internal energy or internal energy into work. So as an example, if I put more weight onto the piston, I'm going to be compressing this, right? And that compression, that work that I'm putting into has to go somewhere. If it's not leaving by heat, then it's going to be increasing the temperature of the gas. And so that's going to be W is equal to negative delta U. And the sign here is opposite because work is being done by the outside. You're pressing it, okay? And remember, pressing it is negative work. So negative work, so that's why it's negative here. And delta U is about temperature change, okay? Now, one more thing that you need to keep in mind is adiabatic process can be used a lot for calculation purposes to test your knowledge. And that's the reason why is because of this special relationship called P times V to the power of 5 over 3 is equal to a constant. Okay, and what this means, okay, I don't want you to get confused, but what this means is when I go from, let's say, A to B, right, I'm going to have here, I have PA, VA, and here I have PB, VB, right? So if I know, okay, initially I know PA and VA, right, because that's the initial point. And if I increase the pressure to B, if I know one factor, okay, let's say PB. If I know PB, then I'm able to calculate VB, and that's using this relationship. So PA times VA to the power of 5 over 4 of 3 is equal to PB times VB 5 over 3. Okay, so isolate one of the factors, and you can easily calculate the that factor using the 3 knowns. Okay. Okay, so let's do this problem. So the volume of an ideal monatomic gas is reduced in an adiabatic compression by a factor of 8.0. Okay, that means that VB is 1/8 of VA, right? Okay, we also know that PA, VA times by to the power of 5 over 3 is equal to PB, VB 5 over 3. So let me rearrange this. If I rearrange this, I know that PB over PA is equal to VA over VB, this. I hope you agree with this. And if I just plug in, VB is equal to 1 over 8. This is just equal to 8 to the 5 over 3, right? And that's equal to 32. Okay, so that means that PB over PA is equal to 32. So for me to reduce the volume by factor of 8, I need to increase the pressure by a factor of 32. Okay, and this relationship holds for any monatomic gas. You're going to learn, in university that this correlation of 5/3 is different for different types of gases. You can have monatomic gases, you can have, gases like oxygen where you have O2, right? Two oxygen being stuck together, or H2, two hydrogen being stuck together. This is true for a monatomic gas for 5/3, and that's the extent that you'll learn in IB physics. Okay, so okay, let's do another, thermodynamic process problem. So give this one a try and pause the video and give this one a try. Okay, so volume of gas of volume of 0.08 cubic meter and pressure blah 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 expands to volume of that at constant pressure when this much of thermal energy are supplied. So first let's identify which type of process it is. Well, we know it's a constant pressure, so that's isobaric process. Right? Iso equal baric pressure, right? B, calculate the work done by the gas. Okay, I already know the pressure is the same, but I know the final and initial V. So work is equal to this. So 4,200 joules. And finally, C, determine the change in internal energy. Well, I know Q and I know W, so I can find out that. So Q minus W is equal to this, which is equal to 7.4 times 10 to the power of negative 3 minus by 4.2 times 10 to the power of 3, which is equal to 3.2 times 10 to the power of 3 joules. Okay, I hope you got the same thing. Let's do another problem. So this one, pause the video and give this one a try as well. Okay, so let's identify the process. So for me to go from B to C, well, I'm keeping the pressure constant while changing the volume. So that's B to C is an isobaric. And D to A, this is isovolumetric, because I'm keeping the volume the same. Okay. B, if CD is an adiabatic process, compare the temperature at points C and D. Now, one thing to note, you can easily identify when something is isobaric or isovolumetric. It's a bit harder to identify when it's isothermal or adiabatic from a PV diagram. If you have like a PT diagram or a VT diagram, then you're going to be able to identify that as well. Okay, so just keep that in mind. Okay, so let's find the temperature at points C and D. If CD is an adiabatic process, compare the temperatures at points C and D. So how do we know if temperature at D is bigger than C? Well, we have to determine whether it's a compression or expansion. And always remember, if the gas is expanding, it's also decreasing in temperature. If you're compressing, then it should be increasing in temperature. Okay, so how do we know which one is compression or expansion? Well, this process, it leads to a bigger volume. If the volume is increasing, then it's a expansion. Therefore, TC is lower than TD, is lower than TC. Okay? Part C, if AB is an isothermal process, compare the temperatures of points A and B. Okay, well, there's totally the answer. It's an isothermal process. Iso, same, thermal, temperature. So if they're isothermal process, then TA is equal to TB. Okay? Let's do another one. Pause the video and give this one a try. Okay, so an ideal monatomic gas expands adiabatically from volume of this to that. If the original pressure was this, determine the final pressure. Okay, so we know it's adiabatic process, which means this correlation stands. So we do that. So P1 times V1 5/3 is equal to P2 V2 5/3. Okay, rearrange this. I want to isolate the final pressure, which is P2. So P2 is equal to P1 times by V1 over V2 5/3. Plug the values in. exact opposite. Okay, and I always want you to make sure after you do it that you know it's logically sound. So right now I'm seeing that pressure decreased. Well, let's check. So if volume increased, then pressure has to decrease. If volume increased, then pressure has to decrease, right? So that makes sense to me, so I think that's correct. Okay, so for B, if we know the final temperature of the gas is 398 Kelvin was a starting temperature, well, this one we can always use the PV equals nRT correlation, right? So P2 V2 over T2 is nR, which is a constant. That means that P1 V1 over T1, that has to also be true as well. So isolating this, T1 is equal to P1 V1 over P2 V2 times by T2. Plug these values in. This one is. This, let me just write it here, 591 Kelvin. Okay, and the reason why I didn't write like, you know, times 10 to the power of 5 times 10 to the power of negative 3 is because see, here is 10 to the power of 5, here is 10 to the power of 5, 10 to the negative 3, 10 to the negative 3, so they cancel each other out, okay? But don't be lazy like me and always write it out just in case, you know, you screw up and stuff like that. So write it out and see if you get the same answer as me, okay? So now I'm going to talk about thermodynamic cycles, okay? We've talked about individually all of these processes, but in real world, it doesn't happen individually. It happens as a collection to, you know, go back as a cycle. So as a perfect example, we've talked about the car cycle, right? So you have the piston coming down, and then as it rotates, it compresses. But during this compression, you actually need to put energy in, right? So you need to put energy in to compress, and then when it expands, you're releasing energy. So, you know, for me to go back to the cycle, I actually have some loss of energy, and then I'm able to generate energy, right? And so this comes back to the whole point of net work, right? You have a work that's negative here and work that's positive here. So the net of this, right, the difference of this is actually what's called the useful work, what's being actually done onto the car, right? And so that's explored in this graph. So for example, work done by gas and expansion is A to B, and work done on gas and compression is B to A. So B to A is here, A to B is here, right? So in the net, the difference between them is this graph here, is this area here. That's what we're actually interested in. And so this touches on, you know, how much energy you put in and how much you get out of it, okay? And that comes to the topic of efficiency. So let's talk about efficiency. So in thermodynamic process, we define efficiency, well, we've always defined efficiency as useful work over input work, right? That's something we've always talked about. So in thermodynamics, what's useful work? That's a W. You know, delta U is not useful work. We don't care about delta U. In fact, we want to minimize delta U, right? And the input work is how much heat we're putting in. In the car's example, it's the heat of combustion, right? How much that fuel lights up and combusts. That's the heat of combustion. So you have W over QH. QH, H stands for hot because in thermodynamics, it's about the difference between the hot place and the cold place. We'll talk about it more in detail in the next video about that, okay? So as an example, you have this graph and this graph, right? So if work in A is 130, work in B is 80, find the efficiency. Okay, so first I need to find the work being done. The net work is actually 130 minus 80, which is 50 joules. Okay, so that's the net work. How much I put in as heat, by the way, this is in combustion, right? So in combustion, I put in 130 joules. This is how much I put in, right? So 130, so the efficiency is equal to 50 joules over 130 joules, because that's the QH, that's the work being done. Okay, and so you notice that the efficiency is quite low, and how you're able to maximize it is really where it's at, where the research is at. So as an example, combustion engines in cars, they're roughly like 25 to 30% efficient. You know, if you include like hybrid system, which is like turning kinetic energy into electricity, for example, in the car, then we're looking at maybe a bit more increase, like 32, 33%. So this whole efficiency is really important in thermodynamic studies. And we're going to take a look next video into something called a Carnot cycle or Carnot efficiency, which is the idealized case. It's not applicable in the real world, but it's an idealized case. And that's how we try to approach that efficiency as being the maximum. Okay. And also next video, we're going to talk about the second law of thermodynamics, which is about the quality of energy and how it changes with every process. So stay tuned for that video. And I'll see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.